What up? It's time for Advent Code Day 7. For part 1, we are to consider bridge repair. When we go to cross the bridge, we notice a group of engineers trying to repair it. The engineers tell us that they need final calibrations, but some young elephants were playing nearby and stole all the operators from their calibration equations. They could finish the calibrations if only someone could determine which test values could possibly be produced by placing any combination of operators into their calibration equations, your puzzle input. So for example, each line represents a single equation right here, and then the test value appears before the colon on each line. So this would be the test value for equation 1, this would be the test value for equation 2, and so on. And it's our job to determine whether the remaining numbers can be combined with operators to produce the test value. So they tell us operators are always evaluated left to right and not according to precedence rules. And they tell us that the two operators we have are addition and multiplication. So basically we want to look at these numbers right here and see, hey, can we insert a plus sign or a multiplication sign here and a plus sign or a multiplication sign here and achieve the test value. For example, right here, we would add 81 and 40 because we're doing it left to right, and then we would multiply 121, which is the value we have so far, with 27 and achieve 3,267. And so this won't be possible for all of the equations. So what they ask us is they say, get the total calibration result, which is the sum of the test values from just the equations that could possibly be true. Let's find out what is the total calibration result. Let's get our input. You can see I have the input saved next to the script, and if I print it to the console, it looks as we would expect. So first let's parse our input. I'm going to make a list called equations, and in it I'm going to save our test values and our nums or our operands. So for each line in F, I'm going to get the test num and the nums by taking the line, making sure I remove the new line at the end of the line, and then splitting it based off of that colon and the space, right? And then before I append it to my equations, I'm going to make sure to turn everything into ints, right? So I'm going to turn the test num into an int, I should say cast. And also I'm going to make sure to save the test num and the nums in a tuple so that I know that they go together. And then I'm going to make the nums a tuple themselves. So I'm going to map each of the numbers in our nums to an int, and I'm going to make sure to split it by space. And so now if I were to print equations, we see that we have a bunch of test values and then the following numbers. Now, how do we actually see if we can achieve the test value using the numbers? What we can do is we can go number by number and try either adding it or multiplying it, since we apply the operations left to right anyway, right? So we need to keep track of a number that we have so far and then what the next number is, and then try both of our operations. And if we get to a number that's too big, we should stop because it will never be able to achieve our test value. Or if we get to the end and we achieve our test value, we should say, hey, we did it. Or if we get to the end and we don't achieve our test value, or if we get that case where it's too big, we should go back and try a different operation. And we do this until we either find that we achieved the test value or we tried every possible combination and none of them worked. This method is called recursive backtracking. And so for part 1, I'm going to put the skeleton logic. We want to have a total that we're keeping track of. And then for each test value and the numbers in our equations, if I can backtrack and achieve the test value from the nums, then I want to add the test value to our total. And then I want to return the total once I've done that for each equation. backtrack is going to return a Boolean telling us whether we can achieve test value with the nums and operations we've been given. And so now the question is, how do we implement backtrack? So what I'm going to do is I'm going to make a function that keeps track of the value we have so far and the next number, and then inserts it using addition or multiplication. So I'm going to make a function that does it for addition. I'm going to make a function that does it for multiplication. I'm going to make one called backtrack mul. This is what I did in competition, by the way. Backtrack mul of, it needs to know what the test value is in the numbers, but it also needs to know what the value so far is and what the next number is. I'm going to keep track of that with an index. And so what are our base cases? If there is no next number, right, if we've exhausted our list of nums, then we should check whether our value so far equals to the test value. And if the value so far exceeds the test value, then we should return false, because that means that we'll never be able to achieve the test value with the given state, right? And so otherwise, right, what I want to do here is I want to try inserting the next number with addition or with multiplication and seeing if either of them works. We know our next val so far is going to equal to val so far times nums I, because this is backtrack mul. And then we can either try doing multiplication again, and we can increment our index to move on to the next number, or we can try doing addition, which should look almost exactly the same, except that we use the addition function instead of the multiplication function. In this case, we could just return it directly because the result is a Boolean. And so now, to implement the addition version, we do the exact same logic, and the only difference is that we obviously rename it, but also instead of doing a multiplication here, we do an addition. And so now, to actually implement our main backtrack that we use in part 1, all we need to do is define a signature, and then try each operation. So I'm going to try A, which is going to be backtrack add, and it's going to take in our test val, our nums, and then for the val so far, we would just start with the first number, and then our next number would be the number at index 1. And we'll do the same thing for multiplication. And then if either of these works, so if starting with multiplication works, we want to return true. And otherwise, we want to return whether it worked with starting with multiplication. So if starting with addition works, then we want to return true, and then if not, we want to check whether starting with multiplication works, and if it doesn't work, then nothing will work. So let's try this out. This is our answer. That was the correct answer for part 1. So before we move on to part 2, let's notice something, right? This is a lot of code, and a lot of the code is doing almost exactly the same thing. You might notice backtrack mul and backtrack add have exactly the same body, except for one difference, which is the operation. You also might think, hey, what are they going to ask us for part 2? They might ask us to add another operation, right? What would adding another operation look like right now? Well, we'd have to add a new case in our backtrack. We'd have to add a new backtrack function for our operation. And then we'd have to go back to the other 2 existing backtrack operation functions and add a case where we insert the new operation, right? So here I just tried multiplication and addition, but let's say they had division. Now I'd have to insert a line for division here, and here, and here. That's a lot of changes. Can this be done better? Yes. We can use something called dependency injection, where we essentially provide the operations that the backtracking should use as an argument. How can we achieve this? I'm going to start by just showing you an example of what I mean by passing in the operations. So I'm going to make a variable called part1 operations here, and it's going to have operator.mul and operator.add from the operator module. And these are just functions that do exactly what you would expect, right? Like if I were to print operator.mul of 2 and 7, we would get 14. So these are just functions, and we're using them as values so we can pass them into our part1, right? So I'm going to change part1 to accept these part1 operations. So down here, I'm going to say accept the operations, and then our backtrack should also accept the operations. Our backtrack should take the operations. And so now we can loop through the operations and try each of them, right? So I'm going to actually move this logic that we duplicate in these two functions into our backtrack function, which means that it's also going to have the val so far and the I arguments. And instead of having just an individual operation for each function, I'm going to just loop through each of them and get the next val so far from it using the operation and then advance. So you'll see what I mean in a second. Let's take this logic right here and bring it over into backtrack. So we need to provide backtrack I and val so far. So I'm going to do that. Val so far and I. And I'm going to give them sensible defaults. So I'm going to give them defaults of none and 1, because if you notice, every time we call these functions for the first time, we use 1. And I'm going to initialize val so far to num0 if it's not provided, right? So I'm going to say val so far equals val so far if val so far is provided. So if it's not, none. By the way, we use is here because we can do a reference check when it comes to none. Otherwise, I'm going to start the value so far out with the first number. And then we can proceed as we normally would, right? If we've exhausted all the numbers, we want to check that we've achieved the test value or not. And if the value so far is greater than the test value, then we want to return false, because that means that we'll never be able to achieve it, right? We want to break out early. Otherwise, I'm going to have to call backtrack using each of the operations. And, this is a lot of arguments, and you might want to shorten it up so you can use something called currying, where you define a new function that has the same behavior as the old function, except the first few arguments are sort of already pre-filled in for you. So in Python, we can use something called functools_partial to achieve this, right? So I'm going to make a helper, and the helper is going to use functools_partial, and the function is going to be based off of exactly the function we're working with, backtrack, right? But if you notice, right, like if we go back to what our code used to look like, every time we call one of these backtrack functions, we pass in test value and nums. And for our new function definition, it's also going to have operations. So instead of typing that over and over, I'm going to supply those right here. Right, I'm going to provide it operations, test eval, and nums. And now, when I call backtrack and I provide a new value so far and a new I, that's all I need to do is pass those two values into the helper. So helper is a new defined function, which is exactly the same as backtrack. It's just that these three arguments, which we're using over and over and over, are already supplied to it using partial. So now all I need to do is check if using any of the operations as my next operation works to make the entire equation get satisfied, right? So I can say return whether any of the helpers using the operation. So we'll say put in val so far and nums I, and get the next val so far using the operation, and then advance to the next number. if any of these work for any of the operations in the operations that were given, then return true, otherwise return false. And this function right here does all the same work that these two functions right here were doing. And now you see not only is our solution a lot shorter, but it's a lot easier to change now, right? So let's check that it's actually working. See if we get the same number. So now for part 2, they tell us, look, there's a new operation called the concatenation operator, where if you get 12 and 345, the two numbers should become 12,345. And so they ask us for the same thing. What's the total calibration result, but with the new operator? And so over here to implement, we're going to reuse the same code. We're going to say part 2 equals part 1. We're going to define our concatenation operator. It's going to take in two numbers. And what it's going to do is it's going to convert each of them into strings and concatenate them and convert the whole thing back to a number again. And now the part 2 operations is going to be exactly the same as the part 1 operations, but it's going to accept our new concatenation operation as well. And now we're just going to print part 2 of the equations and the operations. But we're going to make sure to use the part 2 operations this time. And so if we try that out, we get this result right here, which was exactly the answer for part 2. We didn't have to make any changes to the backtracking function or the part 1 because we used dependency injection. Thanks for watching. I hope you enjoyed the dependency injection demonstration. If you want to solve leak code for me on the daily, I have a Discord server in the description down below. I'll make sure to post the solutions on GitHub. And yeah, have a good one.